In this session, we're going to talk about the Laplace transformation. And then the rest of the term is going to be about just Laplace transformation, guys. Before giving the official definition, I just want to give you an example about, why we need the Laplace transformation or what it does. Laplace transformation is kind of machine, guys. So you can put something into it and then you can get another thing. What we're going to put here, it is going to be the differential equation. And then what we expect to get is going to be an algebraic equation. So here we have the Laplace transformation. So most of the time the left-hand side will be called the time domain or the t domain. And then the right-hand side will be called the s domain or the frequency domain. If you are in EE major, you will see later, how to use these in signal processing or in an advanced classes. If you remember, right, we always talk about such a problem. by prime plus cy, which is equal f of t. And then we looked different combination of f of t. And then, as you know, right, we use the UMC and variation of parameters technique so far for the special cases. But look at if I had this type of function on the right hand side. Let's say I have x squared plus 1, 1x bigger than 1, and e to the 2x minus 2 when x is less than or equal to 1. What do you think? Can I use any of the techniques I have learned for this function? You should be able to say no. Why? This is right a function which is piecewise continuous, and then I haven't learned such a thing. When I have such a function, I can't use all those other functions. UMC was applied for the elementary type of function, sine, cosine, polynomial, and exponential. And then variation of parameters, right, we use it for some other type of function which UMC cannot solve it. But when it comes to the discontinuous function, like this one, right, we need to find out some different techniques. That's why we need a new technique which is called the Laplace transformations. Let me give you the official definition to look at closely. Let's say I have a function on this interval, it is defined, and the Laplace transformations or Laplace transform of f is another function, is the function I'm gonna call by big F, defined by the following integral. So this is the Laplace transform of the small f, which is going to be big F, which will be given by this integral. As in the example I gave it to you, in the machine example, look at it, I put here an f of t, a function, and it gave me another function, but later we will see that that's going to be an algebraic equation actually. And then most of the time, what I'm going to do, I'm going to put here the differential equation, and then Laplace transformation, will transform the differential equation into an algebraic equation, guys. There are some details about the transformation. The domain of big F is all the values of S for which the integral exists And from now on, we are going to use two different notation for the Laplace transformation. The Laplace transform of f is going to be denoted by big F or Laplace of f in this way. Look at that, Laplace of f. So sometimes you are going to see in the examples, okay, I'm going to drop this s, okay, since it's not necessary. Also, we are going to drop the t here, since we know we need to have always the t, and then this Laplace will produce an s function, okay? That's why, okay, to simplify the process, okay, and not to waste some more time on the examples, we are going to drop the s and t. And if you notice that the integral was an improper integral, and then if you remember from the calculus 2 classes, so improper integral can be, right, expressed in this way. So the Laplace of my f of t, right, which I gave in this way, 0 to the infinite, e to the negative st, f of t dt. So I can write this integral by limit plus integral, if you remember from Calc 2 classes, f of t dt whenever the limit exists. Look at that. What it says, this improper integral, why we call improper, since we have the right infinite here. That's why it is improper integral. And an improper integral can be solved not just by using the right integral itself. You need to use limit plus integral, right? So first of all, you need to solve the integral, then you need to take the limit of that integral so that you can get the result for the improper integral. So okay, now we gave the definition, and then let's see, okay, on an example how to use the Laplace transformation. So I'm gonna give it to you, a simplest example for the Laplace transformation. So this is the question. Let's determine the Laplace transform. From now, I'm just going to use LT of the constant function f of t is equal 1 when t is bigger than 0, since the integral rate should be defined for bigger than 0 values. Okay, what am I going to do? So the Laplace transform of any given function, right, should be defined in this way, 0 to the infinite negative e to the st f of t dt. What is my function here, which is just 1, right, which is a constant function. So e to the negative st times 1 dt. What I should do, I should use the improper integral definition. Limit when n goes infinite, 0 to the n, e to the negative st dt. Limit when n goes infinite. I need to take the integral first, as we mentioned before, right? First integral. What is the integral of e to the negative st? E to the negative st over negative s. And then my bounds still there. If I use my bounds, I have limit e to the negative s times n over negative s. Minus, but I have another minus here, if you notice that. It is equal plus e to the negative s times 0 over negative plus s. Since I just spent the negative and then I multiplied, I have positive. Okay, I'm done with the integral. Now it is time to take the limit. The second term here, if you notice that this is just 1, and then I have what? 1 over s term. So how am I going to take the limit of this term? When n goes infinite, as you see, I just have one term here, right? Which depends on the n. since s here is just a constant number, when n goes infinite, this will go 0. So this term is going to be 0 since this term goes 0. And my result is going to be 1 over s, guys. So I can formalize in this way the Laplace of this function, which is 1, which is equal 1 over s, right, when t is bigger than 0. Okay? Let's look at the second example. F of t, I will choose in this way, e to the at. So my question is same. What is the Laplace transform of this function? What I will do, I will use the same integral, which is my Laplace transform. So 0 to the infinite, e to the negative st. This time, look at my function is going to be e to the at and dt. Before taking the integral, I see I can combine these terms in this way, s minus a t dt. Okay, now it is time to use the right improper integral definition. When limit n goes infinite, 0 to the n, e to the negative s minus at dt, and integral will be equal, right? This one, e to the negative s minus at or negative s minus a. And then my bounds are gonna be same, 0 to the n. And now it is time to take the right limit. So e to the negative s minus a, if I use my first bound, it is going to be this one, negative s minus a. And then plus, since I have another negative right from the integral bounds, it is going to be negative s minus a times 0. And look at that, negative plus now s minus a. So I had the similar cases, right, for the other function I just solved. Look at that. Instead of s, this time s minus a, right? It doesn't matter as long as I have n here and then negative. When n goes infinite, this term will go 0, right? And then I just have this term. This will be, again, 1, since e to the 0 is 1. And then the result is going to be equal, guys, 1 over s minus a, when s bigger than a.